There you go. Let me know if you can see it.
Yes, we can.
Good. Okay, welcome everybody. As said, I'm going to talk today about sfnetworks, which is an R package for geospatial networks. How I'm going to do it is I'm going to go through this notebook, which contains both some text and some code. If you want to follow along, there's also a GitHub link where you can find this presentation, and I also put it in the chat a few minutes ago. So if you want to rather see it on your own screen or you want to look back at it when we're done, then you can find it there. I did make some assumptions that I hope most of you know R, and I hope most of you know a little bit what a network is. I think some of you have even already worked with this package, but we're going to start from the basics and explain first why we made this package, why we think it's useful. Then we go through some basic functionalities on a little toy network, which I think most of the mathematicians usually like a lot, before we get to the scary part where we're going to look at the real world network. Finally, I'm going to show some things that are not in the package yet, but that we're currently working on. And I hope to fit this all in 1 hour. Let's see. So to start straight away, the sfnetwork package, also you can find it on GitHub. It's an open source R package, so anybody can use it if you're interested. And it's a package for geospatial networks. So first to show a bit the frame that we're working in, I want to talk a little bit about what are spatial networks. Spatial networks, they are networks where the nodes of the network, they're embedded in space. Yeah, but when we talk about spatial networks, this might also be a very abstract mathematical space, or it might be super small scale space like the human brain, but also very large scale like a star constellation. But with the sfnetwork package, we focus mainly on geospatial networks. Although I think that you might try to analyze human neural networks with the sfnetwork package, and it might work, but that's not really the goal that we made the package for. So we made the package for geospatial networks, and that's actually a subset of spatial networks. And geospatial networks, they're the space that these nodes are embedded in is the geographical space. And the geographical space, this is any location that is on or near the surface of the Earth. But to be said, usually doesn't reach the level of detail as that of these neurons in the brain or processors in the computer or chloroplasts in the leaf. So we're talking, as was already introduced, about road networks, pipeline networks, airline routes, also geolocated social networks. Those are all geospatial networks. And that is what we made the package for. And usually people say that geospatial networks or spatial networks in general, they are not only spatial, but they're also special. But why are these networks special? The main reason actually for this is that the nodes are embedded in space, and it means that for the geospatial networks, by definition, the edges that connect the nodes, they have a cost. Yeah, it's not for free to travel from A to B, and it's not for free to add new edges somewhere. There are a lot of spatial constraints that we need to think about when we analyze geospatial networks. And this creates some special situations, which I'm going to list a few, which are definitely not all of them, but just that you get an idea. Yeah, for example, in many situations, the nodes, they are more likely to be connected to each other when they are close to each other in space. Yeah, because when nodes are far away from each other, there is a high cost of connecting them by an edge in most real-world networks. Yeah. In many situations, space also means that there is a limit to the maximum connections that a node can have. Like how many edges can you have connected to a node in, for example, the street network? These are usually not 100 streets connected to a single intersection, because this just doesn't fit in space. So spatial networks, usually they have different mathematical properties than a lot of non-spatial networks. Also, there are spatial constraints in the way that such a network can grow. And in some cases, when we talk about certain representations or the standard representation of road networks, river networks, pipeline networks, it's not only the nodes that are explicitly embedded in space, but also the edges. They have an explicit embedding in space. Their spatial component is not just defined by that they lead from one location in space to the other, but the road itself also moves its way through space and has an explicit embedding in space. And it means that the shape of such an edge, of a street, for example, can be quite different from the shortest Euclidean distance between its two boundary nodes. Edges might also spatially cross each other without connecting to each other. And sometimes this might be meant, like bridges or tunnels. You will also see situations where this is actually not meant, and you need to clean your network in a way that the connectivity is as you want it. Moving a little bit away from the more mathematical look on this, in real-world geospatial networks, the network itself is, of course, also rarely a closed system. The network is embedded in space, and in this space, in this geographical space, there are a lot of other processes taking place, which themselves are also geospatial. And because of that, we're often asking ourselves questions like, what happens then in the proximity of my network nodes, and what kind of influence has this on the processes that I try to analyze on my network? And this makes that we often do things like spatial joins between the network and other points, snapping certain data points to their nearest nodes, spatial filters. So all such kind of spatial operations we use on the network, which we would not use on a non-spatial network. And finally, which we will also see in this talk, is that geospatial networks also bring along a lot of issues with how do you actually represent geospatial data. You have a lot of different coordinate reference systems in which you can express where your nodes are in space, and you have ways that you can transform between such different coordinate reference systems. So these are all things that make the analysis of geospatial networks special in some sense. As said, I don't say that this list covers everything, but the point I want to make is that just the topology of the graph structure itself does not contain all the information that characterizes a spatial network. And we need to really take the space explicitly into account when we analyze such networks. And this brings us to the reason, why did we actually create the package sfnetworks in R? This is because in R there are very good packages for both the geospatial analysis that I've talked about, also for the non-spatial graph analysis. Which one being the SF package. And without going too much into detail, what it exactly does is that this brings the simple features standard into R. And that means in practice that it allows you a standardized way to represent and analyze spatial vector data, such as points, lines, and polygons. At the other hand, we have the tidygraph package. And the tidygraph package provides what they call a tidy interface to the larger network analysis library igraph. igraph is a library that's written in C. It's very big. It has a lot of functions for graph analysis. And it also has an R package. But the R package of igraph doesn't fit so well into this tidy data workflows. I don't know if you've heard of them, but this is a, let's call it a standardized way to represent data in tabular form and to analyze it, coming from the RStudio company who created this workflow and have a lot of packages that work well with each other in this specific workflow of analyzing data. iGraph, as I said, doesn't fit so good into that, but then tidygraph builds on top of iGraph and makes that those functions fit well into such tidy workflows. And these packages are great. I think they're really good for their purposes. But of course, SF is a package for spatial data analysis, but it doesn't know what a network is. And with some very simple examples, I'm going to show what that then means. Yeah, so we can use SF to create a set of lines, and this set of lines, as you will see in this plot, they share points with each other. Yeah, there are this line here has the same endpoint as this line here. So you could see this as a spatial network where you can follow routes through this graph. But SF doesn't know that. SF just sees this as a distinct set of lines, which you will see, for example, when you would try then, okay, can I compute the edge centrality, so the edge between a centrality, like a standard graph measure of these lines? No, then SF will tell you, I don't know what this is. I don't know what you're talking about, right? And the same goes for tidygraph at the other end, doesn't know about space. So we can, of course, use these lines that I created here, and we're going to tell tidygraph, okay, each line goes from a node to another node, and they share nodes with each other, and then we can just create a table graph object, which is the graph data structure of tidygraph. We can create that with these nodes and edges table. And even the geometry column that stores the spatial geometry of these lines will be in this graph. But tidygraph doesn't really know what to do with those spatial information. It just sees it as another attribute of your edge, which you will see, for example, here, that when we plot this graph, it randomly puts the points somewhere and just draws lines in between them because it doesn't know about space. I can actually show that if you run this again, that it will always put the points at a different spot. Here you see, so if we keep running this, it just randomly puts the point somewhere because it doesn't know what space is, and it doesn't know what the geometry of nodes or geometry of edges is. And just like we showed before with SF, if we ask tidygraph do a spatial filter, then tidygraph will tell me, I don't know what that is. So here we come to the point, why do we need SF networks? The main idea was just to bring the power of these two packages into one and have a general purpose package for the analysis of spatial networks, which can make use both of all the network analysis functions of tidygraph and iGraph, and at the other hand also can make use of the spatial analysis functions in SF. And that you will see now we use the same lines as we created before, and we create an SF network out of it. And there you see the lines are still as they were before, but they are connected to each other by nodes at those points where the lines share an endpoint. And here we can use both, we will say, compute the edge between us centrality of each edge, and it will do it with the network object. And also when we say we want to do this spatial filter on the network, it will also do it and only selects those nodes and edges that are within the spatial polygon that we provided for the filter. So that's the core idea. We have one network object where you can do both network analysis tasks and also spatial analysis tasks. Having said that, we will now go to part 2, where we're going to look into some of the basic functionalities of SF networks. And the first thing I want to do is to look a little bit deeper into the data structure of such an SF network object, because now we've only seen it plotted, but here you see it also printed. So what you see is that in this network, in this toy network that we made before, sorry, this one, we have 12 nodes and 15 edges. And we have one table that stores the information of the nodes, which in this case is only the geometry of the nodes. And we have one table which stores the information of the edges, which is the geometry of each line string, and also a column that says this edge goes from node 1, which is this one, to node 2, which is this one. And this is based on the philosophy of tidygraph, that they say the best way to represent a network within the tidy data structure is to have one table for the nodes and one table for the edges that links to the table of the nodes in one network structure. And in the case of tidygraph, these are always regular tables, but we have them as SF objects where the geometry column is recognized as being a special column. So one thing you see here is that also, of course, we have, like in every geospatial object, a coordinate reference system, which we now in our toy network didn't set because we just made coordinates of 0, 1, 2. But of course, we can say that these are actually real coordinates somewhere in the world according to some projected coordinate reference system, and we can assign our network such a coordinate reference system. I think this is one of the coordinate reference systems used in South Africa. Probably you know that better than me. But we can just say these coordinates are expressed in the according to the coordinate reference system of South Africa, and we will assign this coordinate system to the network. Also, we can just use SF to then transform our network into other coordinate reference systems, also unprojected ones like the WGS84. And you will see that the coordinates change, but they still represent the same points, the same locations, just in a different coordinate reference system. So that is the core data structure that we have for SF networks. And by assigning this African coordinate reference system, even our little toy network with only 0s, 1s, 2s, and 3s has a location in geographical space. Since it's so small, each edge is only 1 meter long, we have to zoom out quite a lot to see where that actually is. And I think it's somewhere in Lake Victoria, where apparently the 0 point of the South African coordinate reference system is located. Yeah. So there you see every geospatial network, if you say in which coordinate reference system your coordinates are expressed, has a location somewhere on this Earth, even our little toy network, which is here. But okay, the structure, as said, looks like it's just like a list or a container of 2 different tables, 2 different SF objects. And it looks like that, but in reality, this is actually not the case. An SF networks in the object inherits the typograph object, which comes from the tidygraph package, and that just inherits a igraph object, which means that an SF network object actually is, let's call it fully fledged graph object, built on top of the data structures of igraph. Just the print method makes it look like you have 2 different tables, 2 different SF objects stored together. However, this is not really the case. It's a real igraph object, a real graph object, but thanks to tidygraph, you can actually treat the object mostly indeed as a list of two different tables, one for the nodes and one for the edges. And that means that you can use all your functions that you know from standard tidy data workflows. I hope some of you know these functions. You can just use them on your network object. You just have to say before, do I want to apply them to the nodes table, or do I want to apply them to the edges table? Yeah, and for that, tidygraph invented what they call the activate verb, the activate function, where you see here that you can say with my network, I first activate the nodes, meaning I'm now going to work on the nodes table, and I'm going to add a column to the nodes table. I'm going to add an attribute to the nodes, which is just a Boolean column, either true or false, randomly. And I can also say I now activate the edges. I'm going to work on the edges table, and I give each edge, I give it a name, and I compute with SF the geographic length of each edge line string. So in this way, you can just use your regular dplyr package verbs within that you're used to when you work with tidy data workflows directly on your network. And here you see the result. We have activated the edges table last, so that one is now on top. It has the column name, and it has a computed geographic length. And the nodes table has this column, this Boolean column called keep me, either don't keep me or do keep me. And we will see later what we're going to use that for. So this is the mutate verb to add new columns to a table. We can do the same with the select verb, which is another common verb from the tidy data workflows. And for example, on the edges, we only want to select the length column. And you see that the length column is here. What you will see, it's not only the length column, because if you have worked with SF before, you know that the whatever column you select, the geometry column always sticks to it. It doesn't go away after a select operation because the geometry is not just a regular attribute. For a graph, also the from and to columns that link the edges to the nodes are not seen as regular attribute columns. They define the structure of the network. So they will also always preserve after a select operation. So here you start to see that some of the verbs that you know, they start to work different when you apply them to the graph, to the sfnetwork object, than when you would apply them to a regular table. Another common verb we have in the tidyverse is filter, which instead of taking a subset of the columns, it takes a subset of the rows. And here we can, for example, say this keep me column that we made is either true or false for the nodes. We only want to keep the nodes that had a true value for this keep me column. Yeah, then we can do that really easily, saying again, we want to analyze the nodes table, so we activate it, and then we use that column to apply a attribute filter to the nodes. And you will see only the nodes that have a true value for keep me are left in the network, which are only 3 of the 12 nodes that we had before. However, again, we're not working on a regular table, we're working on a network object, meaning that we need to preserve the network structure. And that means that by definition in a network, an edge cannot exist when it does not have a node at both of its ends. So if we filter the nodes, so we activate the nodes and apply the filter to the nodes, the edges will always be filtered with them, because otherwise we would not have a valid network anymore. Similarly, some verbs also don't work because tidygraph argues that they break the network structure, and there's not really an equivalent of them when applied to a network. For example, when you're going to summarize the nodes after a group by operation, this standard group by apply combine workflows, that will not work when you apply it to the network, because suddenly you merge all the nodes into one, and it's not clear anymore to which nodes the edges link. Even more so when you would apply a summarize verb to the edges table. This doesn't mean you cannot summarize data from your nodes table. You just have to extract it. In the case of sfnetworks, you can always extract the nodes table as an SF object, and then run the group by and summarize and see how many nodes actually had a keep me value and how many nodes did not have a keep me value. So that is how this network structure fits into the standard tidy data workflows. Then I'm going to move to the next step and show how we can apply network analysis functions to the network object. I will only show a few of them. There is much more to show, but I will of course not go through everything, but just that you get an idea. So the network, as we said, inherits from the typical object, which again inherits from iGraph object. So that means that the sfnetwork object is already understood by all the functions, or at least almost all the functions of tidygraph and iGraph. We can do very basic, standard, common network stuff, like for example, computing the centrality degree of each node. That says how many edges are connected to that node. We just do that again with a mutate verb, which we saw before, and we say the degree of the nodes is the centrality degree, which is a function coming from tidygraph. And like that, you can plot the degree distribution of all the nodes in the network, with most nodes having a degree of 3. You can also, since we're working with spatial networks, put that on a map. The bigger circles, they have the highest node degree, and the smallest circles, they have the lowest node degree. Other stuff that we can do is, for example, converting the network to its minimum spanning tree. That only takes the edges that, like the subset of edges that connects all the nodes with the minimum possible edge length. In this case, our edge weight is geographic length because we're talking about geospatial network. This is also a very common thing to do in graph theory, and we don't need any conversion for that. We can directly do this on sfnetworks objects. Also, we can, just as another example, look at which edges are bridge edges. So bridge edges in graph theory are edges that if you would remove the edge, it would completely disconnect the network into several unconnected components, which in our toy network are not a lot, because there's always an alternative route, as you see, when you would remove one of those edges. Only the edges at the end here, if you would remove this edge, this node here would remain as a single node, as an isolated node, and an unconnected component by itself, and the same yields for this one here. So these are just a few basic examples that are meant to show that you can apply all this kind of common network analysis techniques directly to the sfnetwork object. If you want to know more, of course, tidygraph documentation has a lot of functions. There's a lot you can choose from, just depending on what you need and what you're interested in. And as said, if you don't like the tidygraph functions, or tidygraph doesn't offer something that iGraph does offer, also iGraph functions work directly on, all the iGraph functions should work directly on an sfnetwork object. So that was about the network analysis part that works on an sfnetwork object. The same goes for the spatial analysis part in SF. We already showed before we can do a spatial filter. So here, for example, we have a polygon that overlays a part of our network, and we can use that polygon to say we only want to keep those nodes that are inside that that intersect with this polygon. Here the same goes as for the attribute filter that we showed before with dplyr. If nodes are filtered, edges are also filtered, because an edge cannot exist with a node at both of its ends. Spatial filters is one thing you can do. You can also do spatial joins. Yeah, for example, we have here 2 polygons which have a certain ID. One has ID 1 and the other has ID 2. We can then say we do a spatial join, meaning that all the nodes that intersect with polygon number 1 get the ID value 1, and all the nodes that intersect with the polygon number 2 get the ID value 2, which then shows back here. So this is a spatial join that you can also perform directly on an SF network object. Similarly to the dplyr verbs, there are some functions that we don't support because they would break the network structure, things like a spatial union. But the same yields here. If you want to do something like this, if you want to summarize your data spatially, you can extract either the nodes or edges as an SF object and continue your analysis in that way. Here again, there's a lot more to show than this small subset that I showed, but also the SF documentation is really good and has a lot of functions, which most of them you should be able to use on the SF network objects. So here we are at the end of what I already said, that this was the main idea of the SF network package. Just bring together the worlds of tidygraph and SF such that you can apply all those functions onto one object for spatial network analysis. But as often, the system is more than the sum of its parts. So there are also functions that neither tidygraph has and neither SF has because they are specific to the analysis of spatial networks. So that is the third part I want to talk about, is those functions that we added on top of what SF offers and what tidygraph offers, because they are really specific to spatial network analysis. I do want to stress here that SF networks has always been meant to be a general purpose package. So we don't go very into domain specific functions that are dedicated to like a single application or a single domain. They're meant to be functions that are for general spatial network analysis. And then if you want to do domain specific work, then SF networks is meant to be something that you can build on and create a package that uses SF networks and is then dedicated to your specific interest or your specific application. Okay, again, I will not go through all the functions, but I will show a few so that you get an idea what we're talking about. One thing that we came up with is a process that we called blending. And we called it like this because we see it as we see a metaphor for this process is that you have a lot of spatial points. You have the network, you throw them together in a blender, and that results in one coherent outcome of these two things. What does this mean? That means that you can, when you have spatial points that are anywhere around the network, you can first snap them to the nearest location on the network. This doesn't have to be a node, but just to the nearest location on the nearest edge. Split that edge there and add a new node which contains the information and the attributes of those points. Yeah, so here you see, I should have maybe put a reference plot, but if you remember from before, here there is no node and here there is also no node, but now we have two spatial points around our network and we blend them into the network, meaning that we create new nodes on those locations where that are closest to these points. And the attributes of those points then, if they have any, are then also joined into those new nodes. That is one thing that we thought of. This is a very specific spatial network application that neither tidygraph covers nor SF covers. Another thing, for example, is that we can compute the circuity of edges. And this is what I mentioned a little bit in the introduction, that if your edges are also explicitly embedded into space by themselves, then it might often be that the geometry of an edge, the length of the edge geometry, is longer than the straight line distance between its boundary nodes. It's therefore some kind of a measure of detour. Detour compared to the shortest Euclidean distance. This is also something that SF doesn't really cover because it doesn't know what edges are, and tidygraph also doesn't cover because it doesn't know about space. You will see here, of course, in our toy example, actually all our edges are completely straight. So the circuity for each edge is 1 because the circuity is just the ratio between the length of the edge and the as the crow fly distance between its boundary nodes, which in this case is always 1. But in many real-world networks, it will not be 1. What did I want to show more? Yes, here we have what is very important usually in spatial network analysis is the computation of shortest path. This is not unique to spatial networks, I would say. This is also done a lot in standard networks, but it is usually very important when you analyze spatial networks. And also, tidygraph doesn't put a lot of emphasis on it. It has only one function that does something with computing shortest path. So here's also where we saw a gap of we need to add some functions to a package that make it easier to compute all different kinds of shortest path. So what does that do? It just looks at, okay, I want to go from a node to a node. What is the shortest path on my network? And when we talk about geospatial network, by shortest path, we usually mean the path with the shortest geographical distance or the shortest travel time, if you also know the speed that you're moving at. And we have this function sfnetworks, and when we say we want to go from node 1, which was over here, to the last node, node 12, which is over here, we will find the shortest path, and we will return a tibble, because this then also fits nice into the tidy data workflows. iGraph can also do it, but will return a very different object that's a little bit hard to work with when you are in tidy data workflows, which has one column which says which nodes are in this path. There are in total 7 nodes, and this list will contain all the indices of this node. So that is 1, 2, 3, 4, 5, 6, 7. And there are 6 edges, 1, 2, 3, 4, 5, 6, on this path from node 1 to node 12. Of course, we're dealing with spatial networks, so we can plot this. And here you see this is the shortest path that I already showed. Here we only do it from one node to one other node, but we can also do it from multiple nodes to multiple nodes, and you will get one row with each different path having one row. Just to show how spatial networks can be different from standard networks, because usually when you think about standard network analysis, you would say the shortest path is usually the path that has the least amount of edges, which in this network case is different. We can compute also the shortest path by saying we don't want to use any weights. We don't want to use the geographic length as weight. And you will see that that path is different because this one only uses 5 edges instead of 6, but it is clearly spatially longer than the one that we saw here. Also, what sfnetworks added is that you can compute shortest path not only between nodes in the sense that you need to reference a node by its index, but between any pair of spatial points. And it will find the nearest node to your point and then compute the shortest path based on that. So you don't always need to know the exact node indices. You can compute shortest path by referencing different spatial points. One nice thing to mention maybe is that currently we're also working on implementing a function that can not only compute the single shortest path, but can compute k shortest path. So it can give you the top 10 of shortest path, for example. This is a function that was just added to the iGraph package in R, and we can hopefully soon add it also to sfnetworks. Yeah, so the last part I want to show, there is much more to show, but I will keep it with this, is that basically a bridge to our next section where we're going to talk about real world networks. Because our toy network now, of course, was really nice because it was very clean. all the lines were nicely connected to each other, and there were no weird things or unwanted things to be seen in our network. But as you know, as applied mathematicians, probably, that the real world often is not as perfect as our modeled world. And when you go into the real world, you will see a lot of what I then would call as the opposite of clean networks, which would be dirty networks. And I will first show some functions that we have to clean such dirty networks. And again, I will start with a toy example, but we will see it soon also in the real world networks. Yeah, so instead of creating a very clean toy network, I now create a dirty toy network. Ooh, that looks terrible. What do you see here? Some things that might sometimes be wanted, but sometimes not. And those are the three things I'm gonna focus on now. Is one thing, we have what we call in geospatial network analysis, usually we call pseudo nodes. That are nodes that have only one edge coming in and one edge coming out, or in the case of undirected networks, have only two edges connected to them. That can be useful in some cases. For example, if you want to snap points to the nearest node, it might actually be nice that you still have those nodes here. But when we think, for example, about computing shortest path, it might only make the process of finding the shortest path longer, and this node doesn't have any function in those calculations because there is no choice you can make of I turn left here or I turn right here. So then you would like to maybe take out such pseudo nodes. A second thing that we see here is that we have this edge here and this edge here, which clearly intersect with each other, but there is no node at their intersection, which means we have two disconnected components now. There's no connection from this edge possible to any of the other edges in the network. Again, sometimes this may be wanted. Maybe this is a bridge or it is a tunnel. But there might also be cases where this is actually the result of bad data, and we actually want to add nodes there. And the third thing is that we have here two edges that start and end at the same node. And in many graph applications, this is not allowed because it's not as they would call it a simple graph. In a simple graph, you would only have one edge going between a pair of nodes. In a lot of road networks, this is definitely not the case. But in other applications, we do require that there's only one edge going between pair of nodes. And the same is with loop edges, like edges that start at the same, that start and end at exactly the same node. Yeah, so now we will see some functions that we can use to get rid of those things. So the first thing is spatial simple. A simple graph, I said, is one that doesn't contain multiple edges between the same pair of nodes, and that doesn't contain loop edges. So we just convert our network using the conversion function spatial simple, and we get rid of those edges here. Second thing I talked about was the intersection where there is no node. I will not go through the whole text. I will just show the plot again. This is what we call a spatial subdivision, meaning that we subdivide these two edges into multiple edges by adding a node and connecting them to each other. So you see, when we run that, we suddenly have this node here, and the network is now one single connected component. And the third thing I wanted to show was the pseudonodes. So that we call spatial smooth, because it means that we smooth out a node. And when we run that in the same structure, we get rid of them, and suddenly we end up with a very beautifully looking clean network. So this is just some examples of things that SF networks can do and that they add on top of the functionalities of tidygraph and SF. Again, we also have a documentation website, which I think also contains a lot of information, and there you can find all the functions that the package contains with more examples and explanations of them. Then part 3, real-world networks. We've now only looked at abstract networks that we created by means just to show some examples. But now we go to real-world networks, and the common source for real-world networks and a common open data source for geospatial networks in the real world is OpenStreetMap. I think most of you might have heard of it. It's a crowdsourced map platform that allows you to extract all different kinds of data from these maps. And what we will do here, I'm doing my PhD in mobility planning in geoinformatics. So I'm personally always usually interested in street networks. So I will show a small example of a street network in South Africa. This is the street network in Umtsimkhulu. I don't know if any one of you has heard of it. Might very well be not, but this happens to be a small village where my mother was born a long time ago. So that's why I took it as an example. So to get this data, from OpenStreetMap, we now use the OSM data package, and this is an interface in R that allows you to call what is called the overpass API of OpenStreetMap. So this is an API of OpenStreetMap that you can tell, I want roads in this area with this attributes, and you can make a query to the OpenStreetMap database and get out the data that you want. I made the note here that if you use larger networks, usually it's not recommended to use the Overpass API, one, because it will become slow, but also because you will overload the OpenStreetMap server. So in that way, you can better download an OpenStreetMap file from a specific timestamp, which there is a website called GeoFabric that has a lot of them already prepared, and read it into R using another package, which is called OSM extract. But since we use a very small network here, I'm sticking with OSM data. So here we define what bounding box we want to get the data from, and we extract all the features that have a highway key, which in OSM is a way of saying that it is a street, or a path. These are just lines, just SF lines, and once we extracted them, we can see them on the map. Yeah, so these are all these lines, the street network in a very small village of Umtsimkhulu. If you want to know where it is, I can zoom out a little bit. It is over here in between Durban and Umtata. So now we have a set of lines, and we know already that from a set of lines, we can create a network using sfnetworks. And we can assign it, we can transform it into a CRS that we want, because usually OSM comes with the unprojected CRS WGS84, and we want to have it in the projected South African coordinate reference system. Here you see the network. It has a lot of nodes and a lot of edges, and each edge has some attributes that tell us something about the streets, like what is its surface, what type of street is it, does the street have a name? So when we move on, we can now have it as a network, so we can plot it as a network on the map. You will see already that when you work with OpenStreetMap data, it's not always as clean as you hoped it would be. We see here, for example, that streets obviously intersect. There doesn't seem to be any bridge or tunnel here, but they just don't share a node. We see also here, if I remember well, that this roundabout here is a single edge going around, meaning that all these nodes you see here are actually not connected to this roundabout. So you create a lot of disconnected components here. We also see that we have some pseudo nodes over here, which have just one incoming and outgoing edge. And when we do shortest path calculations, they don't really have a function. So we can use now our cleaning functions that we presented already to real world networks. The subdivision one to put nodes on places where the edges intersect, and the smooth one to get rid of these pseudo nodes. When we do that, we have the network again, but we will see that we now have a node here at this place where I showed there wasn't one before. We have the roundabout over here, hopefully being split into all different kinds of small edges. Yes, this is a different one, this is a different one, this is a different one, and this is a different one. And we got rid of our pseudo nodes that were located over here. So here you see this also works on real-world networks that you can get from OpenStreetMap. You would see that the original network we had 250 disconnected components. Well, our new network, now cleaned one, has one single connected component. All streets are connected to each other. If that's not the case, you can also choose to select the largest connected component if you have more than one. And of course, we always say we need to add the length, we need to compute the geographic length, because that's always going to be used when we talk about edge weights in our analysis. Yeah, so we move now to the analysis. I'm looking a bit at the time. So what we do here is just, again, a simple summary statistic, average, node degree. Yeah, this is just very simple summary statistics that you can do on the network. And they don't only work on the toy ones, they also work on the real world ones. And we can also say, let's create now some random points that are close to the network. As said already in the introduction, network in geographical networks are rarely closed systems. There are always processes going on in its proximity, which we might be interested in. So here we have now randomly sampled 50 points that are anywhere close to network edges. And what we might be interested in is the distances between those points. Yeah, when we would see them as points that have nothing to do with the network, we would use the SF function, st distance, to get a distance matrix of all the points. I here only show the first 5, otherwise it gets too big. But this is the distance from point 1 to point 1 is 0. Obviously, between point 1 and 2 is 2 kilometers approximately. So then you get the Euclidean distance matrix. But now let's say that we know that these points are actually processes that happen, are the result of a process that is limited to the network. And the fact that they're not exactly on the network edges is just because, of course, we have measurement inaccuracies, but also representation inaccuracies where we draw edges by single lines, center lines, instead of the polygonal shape that you actually have in the real world. As we say, now we know that these points should be somewhere on the network, but real world data is always messy, so they turn out to be not. Then we can say we're not interested into the Euclidean distance, we're interested into network distance. And then sfnetworks comes in. Yeah, we don't create the Euclidean distance matrix, but we compute the network distance matrix, which might look very different, using the lengths of the edges as the weight. Yeah. What happens always then is that these points are snapped first to their nearest node, and then we compute the network distance between the nearest nodes of those points. But you see already that sometimes the nearest node can be quite far away. So this brings us to what we talked about before. The blending might be useful here, where we first create a node on the nearest point on the edge, on the nearest point on the nearest edge to each point, such that they always have a node that is as close as possible to them on the network. So that we do here when we do the network blend with these points. You see that suddenly now most points have some node that is as close to them as can possibly be. And we can compute again the network distance matrix, which will now hopefully be more accurate. We see here, of course, that the network distances are much longer when we sum them than when we would look at the Euclidean distances. I just want to mention here, I just wanted to show the example that data can be messy and points are not always located on the network, even though you would expect them to be, or even though you know that they should be. But of course, we could also have, for this example, sampled points that are exactly on the network edges, but then we couldn't have talked about messy real-world data. I was actually hoping to find a real-world data set of points, but I didn't manage in the UMSIMKULU use case, unfortunately. So that's why I work with this randomly sampled points to give you the idea. Then the last part, I will hopefully not take too long, that I just want to mention, because I know that most of you, if I understood well, are statisticians interested in linear networks, in spatial linear networks. And we're going to move now a little bit into a topic where you know much more about than I do personally. But I will just show the options that you have, and then you can see if that's actually useful for your work or not. Because as said, sfnetworks is a general purpose package. And we don't mean to include all kind of statistical functions for point patterns on linear networks. That is an application specific topic where there are other packages that do that much better. And we also don't want to make sfnetworks such a package that tries to cover everything. We try to cover a basic data structure. Other packages can extend it. A package for statistical analysis of spatial point patterns on spatial linear networks is the SPAT-STAT-LINET package. You might have heard of it. And what we do offer then is a good integration with this package. Yeah, so you have SPAT-STAT-LINET objects, and you can convert an sfnetworks, the one that we have here, to such a LINET object. They do have some requirements, like for example, they require the network should be simple, so no loop edges, no multiple edges. And also they cannot handle edges that have curves, so they will have all edges being straight lines. Yeah, but this is then our sfnetworks with one line of code converted to a LINET object. And this LINET object is then the basis for a lot of statistical analysis of point patterns that you can do. I will go to it relatively fast. We can, just to show, we can also convert again back from LINET to sfnetwork. And then you see that all edges now are straight lines. The points we sampled before, which we did above, we can convert them to represent a point pattern in the LINET structure, in the SPAT-STAT package structure. And you see that all the points are somewhere on an edge now, and they represent a spatial point pattern on a linear network. We can do things like testing for complete spatial randomness, which I think should be the case here. We can also fit certain point process models to this point pattern that we created. In this case, a Poisson point process model, and we can use those models to actually make predictions for locations on the network. This will not look like anything useful right now because we just have a completely random pattern, but I hope that you get the idea of what advantages the integration of sfnetworks with the LINET package can give you. You can also use edge attributes to be covariates in your predictive models. For example, the type of street that we're talking about. So this integration with LINET gives, I think, you a lot of possibilities to go beyond the core functionalities of sfnetworks into the field of point patterns on linear networks. So this is a model which will probably not have any significant covariance in there because we have had a completely random pattern, but you get the idea, hopefully. So that was the main part. I do want to say that this integration with LINET is still basic. It can be it can be made better if you want to be part of that. There is an issue on sfnetworks which you, if you want to join in, look at that. So since I'm already over my time, I will go through this very fast, but I just want to stress that an open source package is never done. We have still many ideas. I think sfnetworks can do a lot of cool stuff, but also it can still not do a lot. One thing we haven't talked about at all is that we've only looked at creating a network starting with a set of spatial lines, but not starting with a set of spatial points. And in spatial networks, there are a lot of different ways to create spatial networks starting from point data. One way, for example, is also to create a completely random graph, just having random points inside a bounding box and connecting them to each other when they are within a certain distance limit. We have ways that we can say these points, we create a network that is a Delaunay triangulation, which looks like this. We can also use the same points to create a network that is a Gabriel graph, which looks like this. And these are functions that we're now working on that focusing more on starting from points and not only starting from lines. And the second thing, which you might have already seen throughout the presentation, is that we're working on integration with the ggRAF package, which is basically the ggplot package for network data. First, it didn't used to work with sfnetworks, but this would hopefully give you a lot of more options to make nice visualizations out of these networks. It now requires you to have the development versions of those both packages installed, but hopefully soon this is also on cron and everyone can use it and test if this can become something nice. You can represent edges like arcs. There are all different kind of ways that you can make visualizations out of networks with ggRef. That was it from my side. Again, I think sfnetworks can do a lot of cool stuff, but also still a lot to do. And if you want to be part of it, contributing is easy. Only already opening an issue saying, I have this problem, giving an ID, reporting a bug, that's are all already very valuable ways of contributing. And that will help us a lot. So thank you. I don't know if we have time for some questions. And if not, you can, as I said, always go to GitHub and ask things there. We're very open to receiving any kind of comments and questions. Thank you.
Thank you very much. That was excellent and makes me even more excited about sfnetworks. I think we can probably take a few minutes for questions if people have them. People who need to go can leave. We won't stop them. Yes, David.
Hi, Lucas. Thanks for your presentation. It was very nice, and for your package. I thought I would just mention in the sort of real world aspect, I started playing around with it because we were trying to model warehouse movements. And so I was using R quite a bit at the time, and I thought, oh, well, I'll just model the entire structure of the warehouse using SF. And that turned out to be quite tricky, but it works actually quite well. And then sfnetworks on top, I used your snapping function to snap a routing diagram on top of where the access for each pallet was in the warehouse, so that we had a routing that we could then push to our solvers to find shortest paths for multiple forklifts. So I just thought I'd let you know. It's still a proof of concept, but it worked really well, and it looks quite pretty. So thanks for that.
Thank you. Thanks for letting me know. And if you have any code for it that you want to share, then we're also very happy to see it and see
Yes.
all kinds of applications that are done with the package.
Thanks. I'll try and put something together, because I think the use of this for internal movements of goods and you know, tracking, you know, whether it's in a warehouse or large hospital or whatever, we usually work with road networks, so we're very familiar with the road networks like OSM. But trying to actually build your own network becomes quite tricky. But these tools really help a lot. So yeah, thanks for that.
Thank you. Yeah, it's always also nice. Of course, when you create a general purpose package, I use it myself for some applications that I'm working on, but it's always, I don't know what the package can be useful for. And it's always nice to see that then it's used for applications that we didn't even think about when actually starting the package.
Great, thanks.
Any other questions, use cases, comments? Yes, Ingo.
The idea of the arcs is fascinating for me, because it comes from a graph theory in the background. How is that stored in the soft, you know, as a structure? Is it lots of little edges and then it becomes visualized like an arc?
This, to be honest, I don't know. This is this is really done by the ggRef package, which is written by Thomas Lynn Pedersen, who is also the author of tidygraph and is now working with RStudio a lot on ggplot2. So yeah, I just think I cannot answer this question because I don't know. He will probably know how this is done. Yeah.
Okay. All right.
But yeah, I said this is not part. Yeah, this is not part of the sfnetwork code. This is just that we make ggRef work with sfnetwork, but how exactly the internals of ggRef works, I must say that I don't know.
So within sfnetworks, if there's like that circle that you showed, there doesn't have to be a node at every straight line. It can be just a bunch of edges Because the nodes are meant to be intersections. Is that right? If you pull it from OpenStreetMaps, of course.
Yes, so the nodes are meant to be intersections, but you can also have nodes at points where there is no where there's no intersection, as we showed with this pseudo nodes. So there is no requirement that the node should always be an intersection in the street network.
Thank you. Thank you for the wonderful seminar. We really appreciate it.
So I actually have a question, which is when it comes to subdividing the network, I suppose, how do you account for the fact that you might want to make some intersections into real intersections, but in other cases you have legitimate overpasses or bridges or whatever? Is there some way to differentiate between those two?
Currently not, but I'm working on it because I have the same issue. Of course, when you have OpenStreetMap data and it's well mapped also, then you usually have tags that say this is a bridge or this is a tunnel. So you could say I'd never want to subdivide those edges. Currently, that is not possible in an easy way, but it's something I have on my list because I'm running into the same issues. Just thinking about it loud, what you could maybe do is filter those edges that you don't want to subdivide out of the network, and then after doing the subdivision on the subset of the graph, do a graph join and have them back together. That might work, but I haven't tried it.
Thank you. No, that makes sense. I suppose it would work. Okay.
You get to put your hand up, then find the hand. How big a network? So you were saying that you should use the OSM data function to import OpenStreetMap pieces. What is sort of the limit of, because you were saying if it's too large, we shouldn't do that. How big is too large? So if you do a whole province, I suppose a country is too large, I can believe, but compared to what you did there, how much bigger can you go?
Well, I mean, we have here in Europe, we actually have countries that are super small, which would actually be quite doable, like Liechtenstein or Monaco. But I see what you mean. I think OpenStreetMap itself has some guidelines on this, but I think that also, well, this actually is also maybe interesting to see what SFNetwork itself can handle, because SFNetworks was also never designed to be a package that is super fast, or we didn't code it with that in mind, that it has to handle extremely large networks. So in that, the largest we have worked with is Greater London, which is already quite big. And such a size of network I wouldn't get from the Overpass API. But if you have any middle-sized city, this should all be doable. It does not have to be a super small village. It might though take some time the bigger that your cities get, and then you might see that it's already much faster to get it from a PBF file, so from a downloaded file. But that again gives some more pre-processing, because usually these PBF files, they cover a larger area, and you probably first want to clip them to a smaller area. So it takes some more time to pre-process. So I would say for myself, if it's a middle-sized city, I would do it with the Overpass API. If you get into like bigger cities with more than 1 million people, I would probably not do it with the Overpass API anymore.
Thank you very much. Anyone else? Yeah, so if there's no more questions, then I guess we can finish off and get on with our evenings. And of course, remember that you can always log issues on GitHub, and you can just do a lot of Googling, which is what I did. I ran into multiple problems which were not caused by sfnetworks, but by my own understanding or lack of understanding during my PhD. And I honestly managed to solve all of my problems with Stack Exchange. There's a lot of good documentation and a lot of good help online. So no reason to get stuck when using sfnetworks. So thank you very much, Lucas. This was very, very cool. And yes, I continue to be excited about the future of sfnetworks.
Thank you for having me. I enjoyed it a lot, and I hope it was useful. And yeah, look forward to any contributions or questions that might still come up at any later point.
Great. Thank you very much.
Thank you. Have a good evening.
Thank you. You too.
Bye.
Bye.